So today's webinar is going to be all about failure rates. How to know what failure rates are good to use, how to know if they're appropriate for your applications, how to know if they're too low, they're too high, what's all going on. We're really going to break it apart. We're going to start this webinar off with very basically actually and define what a failure rate is. There's so many different definitions and different ways people talk about failure rates. I want to start at the very basics and talk about what a failure rate is and all of the different ways to obtain failure rates, how to use them, and then how to tell if they are going to be good for your application or not. How to know if they're realistic, if it's too good to be true, if it's not an apples to apples comparison. And then what to do if you don't have failure rates as well. At the end of this webinar, I'm going to spend some time to answer any questions that you may have. I normally get on a roll during my webinar and I don't really take time to stop it and see if there are any questions, but if you do have them, write them in your panel and I will take some time at the end of the webinar to go through them all. I see a couple new people that I'm not familiar with, so welcome. And just to quickly introduce myself, my name is Loren Stewart. I work here at Exida and I'm a CFSE. I've been working here for about 6 or 7 years now. I work mostly with a lot of my mechanical customers, our valves, actuators, solenoid customers, because my degree was in mechanical engineering. So when I give examples, I usually convey back to the final elements. Along with helping our customers get their products certified, I also work with Exida Academy, and I'm an instructor there. I do our trainings, our teachings, our classes, and also these webinars and papers and stuff like that. If you're not familiar with Exida, once again, welcome. We are involved all the way through anything to do with functional safety. So if you are an OEM who builds that ball valve or that actuator that might need help getting certified to different standards, you might need tools, calculations done, consulting, the whole way through to the person that's using those certified devices to protect, to build a safety system to protect against a hazard, or those end users. Once again, we have tools, calculations, consultants, people to help you, and trainings, and from anywhere in between. And that's not just in functional safety, but also alarm management and cybersecurity. I like to say no matter where you are, where your customers are, where your products are coming from, we have somebody close by to help you out with any of your needs. So wherever you are, wherever there might be an issue or a problem, we can get there quickly and help out with anything. One last thing about Exida, and this is something that I'm very proud of. Exida publishes all of the information we are researching, all of our database, our materials, how we do our stuff, our processes, procedures, it's all out there. Excuse my pun, but I like to say that we truly like to be an open book. And whether it's published in books or white papers, these webinars that are free, the blogs, the white papers as well, we have the information that we are learning and continuously updating. We feel that if we're getting that most up-to-date knowledge in functional safety, the best place for it is out in the world. We need to get that information out there to hopefully make the world a little bit of a safer place. But let's get to why you're really here and what you really care about and those failure rates. As I said, we're going to start very general and kind of build our way up to more specific examples and look at generic numbers and everything and how it's going to be appropriate for you or not. So to start off, we're going to say, well, what is a failure rate? And if you've been in functional safety for a while, this might be a review or kind of boring for you, but Stay with me for just a few minutes, I promise. Well, a failure rate is really a number of failures per unit time for a piece of equipment. It is usually assumed to be a constant value, and that's because of statistics in the bathtub curve. And it can be broken down into several different categories. There can be safe failure rates, there can be dangerous failure rates, there can be detected or undetected failure rates, there can be independent or normal and even common cause failure rates. There's even failure rates for no effect failures or enunciated failures. Failure rates are usually or often expressed in terms of the Greek symbol lambda. That's the big red symbol in the middle if you're not familiar with it. And it's usually referred to in the unit of measurements called fits. And we'll talk about what a fit is coming up. So now we know what a failure rate is, but what do the standards have to say? We always want to know what the rules and regulations have to say about these things that we're learning about. Well, it depends which side of the equation of functional safety you're in. If you're an OEM, you're going to be looking probably at IEC 61508. If you are an end user, you're probably going to be looking at IEC 61511. These standards are very complementary of each other. They're just written in different points of view for the OEMs or end users. However, both IEC 61508 and IEC 61511 talk about failure rates. In the previous versions of the standards, they basically said these are what failure rates are, you need to use them in your calculations, and let you go off. However, in both the newer versions of the standards, they have upped their language in, like I said, both IEC 61508 and 61511. They now not only define what failure rates are, but they say the failure rates need to be reliability data used when quantifying the effects of random failures has to be credible, traceable, documented, and justified. Both the standards took input from end users and from the committee members and said that there are still issues, there's still things that are being, failure rates that are being out there. And what really good reliability and safety engineers have long understood, that no matter how good your calculations or your software or your tools might be, if you put in unrealistic or failure rates that are not credible, traceable, documented, or justified, you're just basically fooling yourself. All of your calculations, your efforts are going to be worthless if they're not credible or justified in your application. So hopefully this new language and the stronger language in both the standards will lead to an end of unrealistic failure rates being used in real-world applications. So now we know what a failure rate is, what the standards say they have to be, and how important they are. Now let's take a look at how failure rates are measured. Well, the failure rates are commonly measured in the process industry from the standards in the unit of fits. Depending on who you talk to, FIT could stand for failures in time or failure unit. I've seen them published both ways. But what a FIT is, it's a number of failures per billion hours for a single piece of equipment. And as I said before, those failure rates or those FITs can be broken down into safe, detected, undetected, dangerous detected, undetected, and even no effect external leak failures as well. So if you see a certificate or a device or a component that says it has a failure rate in fits, you can put that in your mind, knowing that's per per billion operating hours, or 10 to the negative 9. So if some component like a washer or a resistor says it has a failure rate of 5 fits, that's going to be 5 fits is 5 failures, or 5 times 10 to the negative 9 failures per hour. These failure rates and fits are very important pieces of information if you are an OEM to be providing to your end users. If you're an end user, this is a very important information to ask for your OEMs. These failure rates can be entered into very important pieces of information, significant portions of your design, like your SIL verification tasks and your PFD average, or your probability of failure on demand average. So it's imperative that the failure rates are not only for the right application, but for the right operation, the right demand, but they're also realistic and correct. So let's take a look at where these failure rates come from. Well, in functional safety engineering, there are 2 fundamental ways to get your failure rates. You can estimate them or you can predict them. Estimation technique is based on looking at field failure data and historical data, where predictive techniques will be either based on test results or design stress strength analysis. And we're going to look at different ways in both the estimation and predictive techniques to get your failure rates. So in estimation, reliability engineering says that you can estimate failure rates from field failure reports using statistical techniques and analysis if the analysis also has a good understanding of the equipment operation, of the component failure modes, of all key environmental variables, of how the equipment's being used, on how the data is being used by the designers. You need to know more than just the number of returns or the number of shipments. The 3 main estimation techniques are manufacturing field failure device studies, industry databases, and end user field data studies. Just like with everything in life, there are positives and negatives with each of these estimation techniques. Same thing with the predictive techniques as well, which we'll talk about next. First of all, the first way of estimating, the manufacturing field return data studies. This can be very great information if the data is collected, it's collected correctly, and root cause analysis is done. However, that's not always the case. We have seen some manufacturers' field return data studies where it was simply a look at the number of, just the count of the number of items returned without more information. Another thing to keep in mind, depending on manufacturers to manufacturers, they might have a different definition of what they count as a failure. We've seen some instances where one company marks everything as customer misuse and doesn't count it, whereas a different company counted every single return that came in. Some companies may not know the actual percent of returns that are actually given to them. If you're a cheaper part in the CIF, you might not always be called. It might just be easier to take a new one off the shelf and put it in. But if there is enough data on that specific manufacturer, specific device, that is a gold mine of information if you're doing the root cause analysis and seeing what the problems really are. The next way of estimating failure rates is from historical data from industry databases. And these industry databases, once again, they can be very valuable pieces of information. Normally, they record all failures. They don't care how it was done. They just care that something failed. And it's usually compared with detailed taxonomy and operating conditions. And hopefully with as found error conditions as well. One of my favorite industry databases is the IRIDA database. I've done a lot of studies with their work, with their field and their books, how they're doing their operation, and they really have some great detail. However, one of the issues with an industry database is you want to make sure you're doing an apples to apples comparison. As I said, IRIDA, that's a wonderful one. However, it's normally for offshore or subsea in the North Sea. If that's not going to be the same type of application you're in, those failure rates might not be the best for your calculations. If you are a valve operating inside a factory with clean conditions, you might not be experiencing the same stresses or the same issues that a valve a mile below the North Sea might see. And then final way of estimating failure rates is end user field failure data studies. Once again, this is kind of similar to the manufacturer field data studies. You don't know which end user is going to classify something as an issue or not an issue. There's many times where something can be recorded as a systematic issue and brushed under the rug and not counted in a failure report. Another issue with end user field failure data studies are that many data collection systems aren't very strong. They aren't recording as found conditions. They're not having operating conditions. They're not looking into all of this information. If you do have a strong data collection system, this can be, once again, a gold mine of information. This can lower your failures. You can really dig into what's going on in your company. However, with all three of these techniques, one thing to keep in mind, this is all historical data, and you need to have a good understanding of the operation, the environment, the profile, the demand, and how the equipment's being used. Just doing the calculations and doing the math is not enough. You have to do more. You're not just doing a calculation anymore. Expand your mind into engineerings. The other way of looking at failure rates is predicting failure rates. Just like with estimating failure rates, there are pros and cons with both of these methods. With a pro for both predicted methods is that you don't have to have that historical data to do these. This is especially good with software electronics that seem to be changing more often than maybe a simple ball valve would. So the predictive technique you can do on new designs or old designs. The one way of predicting failure rates, the first way we're going to talk about is the B10 method. And the B10 method is also known as cycle testing, and this is done for high demand or constant or dynamic operation applications. It is a testing setup that has at least 20 products going, and 10% of those, once 10% of those fail, that would be the B10 point, you can predict the failure rates from that. one thing to keep in mind is that that cycle testing or that B10 data is for that constant dynamic operation. So if you're in the process industry or in a low demand mode of operation, this is not going to be an apples to apples comparison for you. There are things in low demand like stiction, cold welding, corrosion that creep up when you're not constantly moving. The B10 data point assumes that the only failures are premature wear out and nothing else will happen. The other way of predicting failure rates is the FMEDA technique. That stands for Failure Mode Effect and Diagnostic Analysis. And this is looking at design strength versus all of the stresses for a predefined environment with a predefined device. When the FMEDA is done, we get a bill of material and a drawing of the device, and we look at every single way we can possibly break each component. We look at all of the stress levels of that specific design with that specific application and environment. So we would do an FMEDA on a manufacturer's ball valve or pressure transmitter or sensors, down to the manufacturer's series, make, and model. It's going to be based on the design and the parts that are used, any design margins. We're going to look at any automatic diagnostics, look at how it's being used in the environment, how the device will be deployed. And then we can use the component failure rates, the individual component failure rates, and add them up and to predict the product failure rate for the overall device. With the FMEDA, this product failure rate can be split into that safe, dangerous, detected, undetected, no effect failures, external leaks. All of those can be pulled apart by the FMEDA technique. Along with all of those different product failure rates, you're also going to know all of the product failure modes and the diagnostic coverage. One thing, a negative thing with the FMEDA is you have to be considerate of what the component database is for the FMEDA. With the component database, just like we explained earlier, if you're using bad numbers to go into the technique, you're going to get junk coming out of the technique as well. So we'll talk about a little bit about the component database later and how important it is, but knowing that you have a component database used for the specific application, the specific environment, and how it's being operated is very important. This is because a failure mode might be dangerous in one application but is safe in another application. If you think of a valve that opens on trip or closes on trip, a failure of being stuck open or stuck closed or not able to open or shut could be safe or dangerous in the different application or operations. The FMEDA method is looking at that strength of the design. Once again, it can be a newly designed device or an old designed device, and we took a number of techniques and combined them together. FMEA, look with diagnostic analysis, with the military handbook 217, and all combined to look at how the parts could possibly fail when different stresses of the environment are thrown at it, considering their diagnostics. So using a series system concept, the failure rates of both old and new designs can be predicted knowing the failure rates of each component that goes into that device. So we're going to look at a set of stress and strength factors. And these failure rates, the failure modes, the diagnostic coverage, useful life, even proof test coverage can be predicted by the FMEDA study of the design. And depending on your environment, depending on your application, low demand or high demand mode, you will have different stresses and strengths coming into your analysis. So those are all the ways that products get failure rates. Well, how do you get them for each product? Well, if you're an end user and you're using certified products, that's easy. You just ask for the certificate. On the back of the certificate, there's going to be listed the failure rates you need, broken down into safe detected, safe undetected, dangerous detected, and dangerous undetected failure rates. If you don't have a certificate on hand, you can easily look on the SAEL website and search the different types of devices you're looking for, or the manufacturer, or the name, and you can simply pull up those certificates. If you're not using certified products, that's okay. You can still get your failure rates. Go back to whoever's making that product and ask if they have an FMEDA report or failure rates for this product. Even if they didn't go through the whole certification, they might have failure rates. But it's very important to make sure you're looking at apples to apples. Make sure you're the same environment, application, demand mode, operation. Ask how these failure rates were achieved. Was it through estimation or predictive techniques? Either way can be acceptable. Just know what you're dealing with. So once you get these failure rates, how do you know if it is appropriate for your application or not? I like to always refer my customers to silsafedata.com. I call it my sanity check, where when I don't know where to go for something, this kind of helps me out to keep me in the realistic failure rates range. And I know you can't read this carefully, but each device is broken out into a general category and given a low bounds and a high bounds of failure rates of what you can expect. And some of these bounds are really large, and some of them are a little smaller because we don't know all of those pieces of information, like the environment and the complexity of each device. So let's zoom in and take a closer look. This is an example of one we actually received kind of recently. We have got a certificate, and it was from a manufacturer's return data method for a actuator. And they said for the entire actuator, the failure rate is 17.3 fits. We know that that's pretty small. That's 10 to the negative 9. Okay. So we weren't sure how we felt about this. So we went on to silsafedata.com and we looked that this is a Scotch yoke actuator, and on Silsafe Data, they have information on both spring return and double acting. This example was a spring return, so I could see that I should expect a failure rate between 400 to 1250 fits. It's typical. Well, there always are exceptions to the rules, but when it's more than an order of magnitude different, that's when I start to question things. Is this the best actuator that's ever been made in the world? Really? So looking at this exact same model, same make, everything, a FMEDA, a calibrated FMEDA was done on this with a calibrated component database, and it was found that that same actuator was actually predicted to be 600 fits. As you can see, I kind of feel better with that 600. It is on the lower side, but this might not have as many O-rings, or it might not be as complicated. There might not be as many ways to leak or have dangerous failures or bind. And I'm not sure what the environment is, if this is open on trip or close on trip. All of that can play a part in this. However, when I get something that's way, way below what is typically seen in industry, that's when I'm not saying reject it. I'm saying let's start asking a lot of questions. So remember when we talked about who cares about failure rates? What do the standards say? Well, they said they need to be credible, traceable, documented, and justified. So if you think of your standards, whether you're dealing with IEC 61508 or 511, I like to think of it as this bridge to safety. It's giving you these opportunities to get to the other side with a safer place. But if you start cherry picking what you feel like doing or what you want to turn a blind eye to, you're just fooling yourself. You might not be taking away a main support, but cherry pick enough. Do you really want to be walking on that bridge? This is what optimistic failure rates are. Optimistic failure rates might not seem like a very big deal. You know, the tiny, tiny numbers, 10 to the -9. However, they go into very important calculations, and that data can lead to unsafe designs. What if that data led to a design that doesn't have enough redundancy? What if that data led to a design that doesn't have enough proof testing, or not doing a foolproof test, or often, as they really should? You're not actually meeting the required risk reduction, and you might not even be achieving the SIL that you think you're going to achieve. I always like to go back and say, when you're designing with possibly optimistic or unrealistic designs or data, I always say, do you want somebody you love right next to that dangerous condition that this device is protecting against? Are these numbers too good to be true? So I'm a very visual person, so I like to put colors and everything on graphs. So I did a solenoid comparison. We looked at a bunch of different solenoids, different types, both poppet and spool. We looked at different databases, like ARETA, field data from a pipeline database, chemical databases, different FMEDAs, and saw that depending on the complexity of the device, there was a little bit of variation. But then we also saw a second grouping, and we wanted to see how that fell in with SIL-safe data. Now, as I said earlier, there are two major different solenoids on this comparison, but the databases we were working with didn't specify which ones were which, so we wanted to show both the spool and poppet solenoids together. However, we noticed that a bunch were falling, once again, way under order of magnitudes. So we did some digging. Some of these were from field failure device. Some of them were from just cycle testing or using non-apples to apples, a high demand and a low demand application. But once again, you can kind of use that sanity check to see where you fall along the typical industry. Now let's go back to the bigger picture. Why does this really matter? Well, why do we need these devices and these safety systems to begin with? Well, it's to prevent serious and potential deadly disasters. These are, unfortunately, are three of the most famous ones that people were killed and injured. There were massive fines, huge cleanups, downtime, huge damage to companies' reputations. when we think about functional safety and we think about failure rates, we just think, oh, yeah, we have to do a calculation. These numbers are 10 to the negative 9. They're so small they don't matter. But at the end of the day, each device is protecting personnel, environmental, and financial risk. So think back to that bridge of safety. You don't want to cherry pick which pieces of functional safety you're going to use. Once again, I really like examples. So if you're not familiar, this is a little of our Excellentia tool. And I just put together a very quick CIF. 1 out of 1, I just picked sensor, logic solver, solenoid, valve, actuator, put it all together and ran some quick calculations. And I used information from final elements of a valve, an actuator, and a solenoid from overly optimistic data that I was given saying, can I use this? Is this good ideas? So when I put together my CIF, I was really excited. You can see that our failure rate for the final elements, the valve, actuator, and solenoid together, is 12.1 fits. Wow, that's really great. With our calculations, we found out that this safety function achieves a SIL2 with no redundancy and no diagnostics needed. So you can just put one of these out there, basically clean your hands of it, never check on it. This is great. You might just be the best safety engineer in the world right now. You look up into the corner, our pie chart that shows PFD average, and you're seeing something a little bit funny. It's showing that all of your final elements only take up 5% of the PFD average. So the PFD average is that probability of failing dangerous on demand. And typically in industry, we see the simple mechanical devices, those final elements, taking up more than half, usually 70% of the PFD average. So this is funny that this CIF is saying actually the sensors are the ones with the least reliability. The sensors are going to give you an issue. So then I decided I'm going to keep the sensors, the logic solver, everything the same, but this time I'm putting in realistic data for our valve, actuator, and solenoids. So now our final elements come out to a 1,300 fit instead of, what was it, 12 fits. So you can see that's an order of magnitude difference. Unfortunately, in this case, our SIL level for our PFD average has dropped from a SIL 2 to a SIL 1. But don't freak out yet. There are ways, remember we only have, this is a 1 out of 1. We can introduce redundancy, we can add no diagnostics, we can introduce, implement diagnostics. There are still things that you can do to get back to that SIL 2, so don't freak out. But look back at that pie chart. Now it's showing that the final element is that main contributor to the PFD average. That makes a lot more sense in what we typically see. So I know it might be harmless to think, well, these numbers aren't that big of a deal, they're so tiny. But just remember what that CIF is protecting against, and using optimistic data is just introducing a ticking time bomb, just waiting. It is simply just unsafe. So now I've scared you. Now I'm going to help you feel a little bit better. What do you do if you don't have good data? What if you've gotten these information, either it's unrealistic or it's not for the same environment or operation? What do you do now? Well, first of all, you can always use generic numbers in your SIL verification calculations. These will be conservative numbers. They will be higher than certified devices. However, that's not necessarily a bad thing. This is going to be because if the device is not certified or not correctly identified, then you don't know the high quality or the protection against all the different failures. and all of the things that can be prevented against. So you can always use generic numbers in your calculations. I say if you don't have generic numbers, you can also go back to silsafedata.com. Silsafedata.com was built off of multiple different databases: the ARETA, chemical, field failure, power, statistical analysis, the predictive analysis, the EMCRH, field failure reports, to all calibrate that SIL-safe data and to give those failure rates. So this was just one example I've had recently. I had somebody come up to me and say, well, we need a motor controller. We don't have information on it. We're not using a certified product right now. It's something that we need to get to in the future. However, we can't do that right now. What do we do? And I said, well, you can always use that upper limit of silsafedata.com as kind of that generic result. Once again, it's going to be more conservative. It's going to give you those higher numbers. However, without knowing everything about the operation application, you can't use something lower than that, unless you go back and look at failure rates, FMEDAs, or any of that. And that's also an option for you. If you ever have a device and you need failure rates, you can always do an FMEDA analysis for the device. We have had customers do that as well. So I was bad throughout the webinar and did not take time to answer any questions. Oops, where'd the Wando go? So I'm going to take some time right now and go through it. If you have any questions later on afterwards, please feel free to email us or check out our website. Like I said, we have great reference material. We have blogs and webinars and white papers that are free to download and view as many times as you want. And if you really enjoyed this and you want a lot of more information, we have courses that are online and in person that are a few days or even a full week. And if our most popular ones, we started doing online as well, so you can train at your own pace from your own home. Okay, so let me go ahead and look at these questions. So what is the difference between a fit and a mean time to before failure? So a fit is going to be, once again, in those 10 to the negative 9 hours, it's going to be in that unit of measurement. Fit is very specific for that 10 to the negative 9. Mean time before failure can be in different units of measurement. It's going to be looking, it's more of looking at that time before a failure occurs, either safe or dangerously. So it can be looked at using those safe or dangerous failure rates as well. The next question, as an end user should be asking for fit for which instrument components? I always suggest every single piece of equipment operating in your SIF needs to be considered. When it comes down to functional safety, it is the weakest link is going to cancel out every good thing you did. So you can have the top of the line everything, and if you just have one piece of equipment that isn't meant for this application or isn't the greatest, that one device can take out all of your other equipment and just make it useless. So ask for failure rates for the sensors, the controllers, the final elements, even mounting and bracketing, piping and tubing, all of those will make a difference. Okay, the next question we have is about some of those databases that we were talking about, such as the FMEDA database and the B10 database. The B10 database isn't necessarily a database per se. That's more of a testing done on pieces of equipment, an analysis done from that. The FMEDA database, I can talk to the one that exida uses. We have a calibrated FMEDA database. We are continuously updating it, and we actually do publish our components. It's in our tools for everybody to see and use. But most of the time, as an end user, you will not have a lot of that information. That's why I always say look at silsafedata.com to kind of use that as your check, and if some things don't line up, then start asking questions. Say, where did you get these failure rates from? Is this for low demand? Is this for the correct application? The next question is from my experience when we're looking at SIS instrumentation. What has certificates? Just some sort of things, or do all of them have them? Well, that's a good question, and that's a question that's actually changing currently. When I first started in the industry, we were seeing a lot of logic solvers, and we were certifying a ton of logic solvers. And we were getting questions from our mechanical customers, well, I don't have software, I don't have sensors, I don't have electrical equipment in my valve. It doesn't need to be certified, right? And that was about 5 years ago that the switch started being seen in the industry that simple mechanical devices need to be included in that. Now we're seeing an even greater upswing. Like we said, that the weakest link can tank your whole SIF. So now people are looking at failure rates for the coupling and the bracking and the mounting. Because if you're just going to a person that's throwing on a piece of sheet metal instead of actually engineering a mounting and coupling, that could undo all of the great you're doing with your final elements. I have a question, and I'm not quite sure what is meant by this. So if you'd like to, I'm going to read it out loud. If you'd like to clarify it, or re-ask it, or explain it to me. I'm sorry, I'm not getting the point. The question is, what is the best rate we can be asking in tender specification? I'm not sure who you're which failure rate you're looking for and who you're asking for that. Okay, thank you for clarifying. Oh, that's something else, sorry. The next question, while I get that clarification, are all of the individual components of an actuator, for example, tested in the FMEDA for all conditions? Not necessarily. So when we are doing an FMEDA, we don't actually physically test the actuator. We are testing it through FMEA techniques and stress strength type of calculations. But we can do the analysis for any conditions that the OEM thinks that valve or that actuator is appropriate for. So, for example, if that actuator could see corrosive environments, if it could see clean environments, severe service, if it could be hydraulic, if it could be air, any way that that actuator with that valve, solenoid, logic solver sensors, any way that it's supposed to be used, we can analyze it. However, there are times where we have a valve that is only used in a severe service, so we only analyze it for those conditions. Or it's never supposed to go in that severe service, so we will not have failure rates for those type of conditions. But when we look at the actuator itself, we look at everything, every nut, bolt, screw, seal, every single thing in it, and see if that bolt shears or breaks off. Can the actuator still do its job? Can it take it to a safe state if needed? At the end, we add up all of those safe failures from every component, all of the dangerous, all of the detected, and all of the undetected failures, and that's how you're given a product failure rate. Okay, so the next question we have is, certifying products and using FITs mandatory for all devices and components? It depends what you consider mandatory. By the standards, you need to consider everything that is going into your CIF. If you consider mandatory by law, depends on what country you are in and how they are evaluating it. If you are considering mandatory by your company or an end user, that's going to be up to that contract. So it is different for many different applications. However, when we're talking about the standards, we need to consider all the components to have failure rates. It is not mandatory that all of the components have certificates, though. You can use failure rates for non-certified devices, absolutely. However, you will not be knowing the systematic capability for that CIF then. We have another question about who issues certificates. There's a couple people that issue certificates. It's kind of whoever the OEM goes to for that. We are one of the leading certificate vendors, I guess. So we do issue certificates. That's one of the things I help my customers with. So I'll meet up with a valve or an actuator company, and I will explain to them all of the requirements of the standard and help show how they meet it. There are other companies that do that as well. So you can look up different certificates. If you want to look at some certificates, I highly suggest the SAEL. It has more than just the exida certificates on them. And then we also got a clarification about the one question we had earlier about the failure rate, what is best to use. And unfortunately, without knowing a lot more information, the type of device, the operation, the application, all of that, I can't answer what failure rate to be using for that. If you want to email me more information, I can help you out and show you where on the SAE or where on the SIL-safe data is a good range to kind of approximate. As of now, that's all the questions we have. So thank you all so much for joining the webinar, and have a great day.